If you're an engineering student, you know there's this huge gap between the physical world and, a digital processor. How does a machine actually feel anything? Well, the answer is a process called transduction. And today, we're going to break down how we translate all these physical things into the electrical signals that make our entire technological world tick.
All right, here's the plan. We'll start with the basics, get our definitions straight. Then we'll look at the step-by-step process. After that, we're diving into the nitty-gritty physics, checking out two really key designs you use every day. And then we'll zoom out to see how it all fits together in a complete system.
Okay, let's kick things off with a pretty fundamental question. It might sound simple, but seriously, the answer is the foundation for pretty much everything. Robotics, consumer electronics, you name it. I mean, really think about that. How does your car's parking sensor know there's a wall there? How does your phone's screen know exactly where your finger is? Or, how does a medical device take the physical force of your blood pressure and turn it into a number? The answer to all of that is the same core concept. Machines are built to perceive a huge range of physical stuff. They can measure heat, sound, how close things are, and force. They're basically the sensory inputs, right? They provide all the raw data for every smart device we have.
So, the answer to our big question? It all comes down to this critical little component called a transducer. At its heart, a transducer is just an energy translator. That's it. It takes one form of energy, like the mechanical pressure from your finger, and it converts it into another form, which is usually an electrical signal a computer can actually understand.
Okay, so you'll hear people use sensor and transducer almost interchangeably, but for an engineer, there's a really important difference. A sensor responds to a physical thing happening. A transducer converts energy. So this means that every single sensor is a transducer, but not all transducers are sensors. A perfect example is a speaker. It's a transducer for sure. It turns electrical energy into sound, but it's not sensing anything, is it?
And just to get even more precise, let's talk about a sensor versus a detector. A sensor gives you a proportional measurement, so think of a thermometer. It tells you the exact temperature. A detector, on the other hand, it's just binary. It gives you a simple yes or no. That car proximity alarm, that's a detector. It's either on or it's off. Simple as that.
So we know a transducer converts energy, but how does that actually work? It's not just some kind of single magical step.
Yeah, it's really important to see transduction as a chain of events, not just one thing. It kicks off with some initial energy input, what we call excitation. Then that physical thing gets converted into some kind of intermediate form before finally spitting out a measurable output. It's a whole conversion pathway.
This process is basically a three-step chain reaction. First, you have the excitation. That's the physical thing you want to measure, like a force. Second, the conversion. That force might cause a material to bend or deform. And third, you get the output. That deformation generates an electrical charge. And boom, that's your signal.
All right, let's get into the real engineering and see how this energy conversion actually works on a physical level. This is where the theory really starts to meet the hardware.
And here's a really key insight. Transduction is not just a one-way street for sensing. These exact same principles of energy conversion are also used for actuation, making things move. So it's the foundation for both input and output in the physical world.
So, broadly speaking, we can lump electromechanical conversion into two big buckets. You've got multi-component methods, which use action at a distance, think about magnetism, but we're going to focus on the other kind, deformation-based methods. And these are so cool because they rely on changes in the material's own physical properties to create a signal.
So within those deformation-based designs, two are absolute crucial, especially when we talk about modern microelectromechanical systems, or MEMS, and those are capacitive and piezoelectric transducers. The fact that you can make them incredibly tiny makes them essential for everything from our phones to medical implants.
You use this technology dozens, probably hundreds of times a day, and you don't even think about it. Seriously, every single time you touch your smartphone, you're kicking off a capacitive transduction event.
So your phone's screen has this grid of electrodes, and they create a stable electrostatic field. Your finger, because it's conductive, messes up that field when it gets close. The system detects that change in capacitance at a very specific point on the grid, and bam, it registers it as a touch. It's so simple, so elegant, and it just works incredibly well.
All right, next up is the piezoelectric effect, and this one is just wild. Certain materials, like quartz, have this amazing property. When you physically stress them, like you squeeze them, they generate an electrical charge. And that charge is directly proportional to the force you applied.
This makes them perfect for super precise force sensors used in research and advanced manufacturing.
Okay, so we've gone pretty deep on the transducer itself. Now let's zoom out a bit and see where this tiny component actually fits into a complete, functioning system.
See, a transducer is just the first part of what we call a closed-loop control system. It's the sensing unit, the system's eyes and ears. That unit sends information to the controller, that's the brain, which then tells the actuating unit, the muscle, what to do. It's this continuous loop of sense, think, and act.
And this is exactly where the electrical and mechanical sides of mechatronics really come together. The signal that comes straight from a transducer is, well, it's raw, it's usually noisy, it's weak, and before the system's controller can do anything with it, that signal needs to be cleaned up.
This whole cleanup process is called signal conditioning. First, you take that raw signal, which might be tiny, we're talking just a few millivolts, and you have to filter it to get rid of all that random electrical noise. Then you amplify it, boosting it up to a more useful voltage level. Finally, for most modern systems, you take that clean, amplified analog signal and you digitize it. Turn it into the ones and zeros that the microprocessor can actually work with.
Which, brings us right to the heart of engineering design. When you have to pick a transducer or even build one, what are the things you look for? What separates a good design from a bad one?
Well, it always comes down to that classic engineering trade-off, right? Performance versus practicality. You absolutely need linearity, so your output is predictable. You need a clean, low-noise signal for accuracy. But it also has to be reliable, it has to be affordable, and it has to be small enough to fit. Hitting that sweet spot is the real challenge.
So, the next time you touch a screen or you see a robot navigating a room or use any kind of medical device, just remember, it all starts right here, with transduction. This whole process of translating the physical world into data, it's not just some topic in a textbook. It is the fundamental building block that lets us give our machines the senses they need to build our future.